Testing 1, 2, 3. Testing. I'm testing my camera. I wonder if it's working. Sorry. Oh, hi. Someone's watching from Japan. Wow. Must be early in the morning. What time is it in Japan? CXC06033. Hi. Okay, so it's working. Cool. Oh, Jack Alexander Model. Ah, so I know you're a viewer. Ah, that's good. Yeah, Jack Alexander. He's the smartest engineer. It's interesting. Jack Alexander did not have a college degree. He was a Navy. Uh, he got his training from the Navy, and he was basically a technician and got all his training from the Navy. But he was more than a technician. He understood it at a very high level, and he would get into arguments with degreed engineers, and then they would throw the math, and then that's where he couldn't uh, compete, or I guess compete, I guess. So he fixed that. He went to school and he got 30 hours of nothing but math. He didn't take the electronics because he already understood electronics, but he needed the math. And once he got the math in there, there was no one that could touch him. I mean, there were people with PhDs, and he was the best. So, yeah, how he came out with that model, he never did tell me. He came out with it in 1969. He used to work at Data Point, which is was a computer company here in San Antonio, Texas. And I think he started building uh, switching power supplies there. And since he probably had one of the very first personal computers, and he wrote a program where he could simulate circuits. This is before Spice, way before Spice. So he was very brilliant man. I got a chance to work with him for about 3 4 years, and and actually he was already retired. He was 80. I think he was 80. He was still working, and I think he died when he was 84. So those 4 years, I learned his modeling technique, and I had asked him if he ever published it, and he never did publish it, and that's why I started teaching his model. I wanted to give him credit. So what do y'all do? CXC06033. Are you engineers too? Japan has very good engineers. Japan in the 70s and 80s kicked our butts. Oh, you are an engineer. Yeah, I used to be a TV repairman. I started in 1980. I was 18 years old. And the televisions back then was, I used to work for RCA, fixing televisions. And Sony, the one and only Sony, started making impact, started selling here in the US. And their televisions were very advanced, very advanced. They were difficult to fix because they were. Uh, oh, Marina! Hey, how you doing, Marina? I'm sorry, guys. Marina Otazu. She's one of my students. I hope you're doing fine. She's Marina is a she just graduated with her bachelor's. She's a, she is a extremely smart young lady, and she's also a very pretty lady. So she's got brains and she's got the looks. I hope I'm not embarrassing you, Marina. So Marina contacted me. She needed some help with modeling a power supply, and I just helped her a little bit, and she actually built a power supply with current control, and man, she did a really good job. And then she wrote. It looked like a report, but it was more like, in my opinion, it looked like a thesis. And this is for a bachelor's, so she did really good. Anyway, I hope you're doing well. I hope your family's doing well too. And last time you told me you were gonna go get your. Oh, you want to know more about me? I was just telling some of the guys. What do you want to know? Does y'all have any questions? I guess career wise, how to. I'm 61 years old. Getting to retire, getting ready to retire, maybe in 2 years. Yes. Okay. What do you want to know specifically, Marina, or anybody else? CXE 06033. How? Okay. How I got started? in electronics or what interested me. That might be an interesting story. Okay. I hope I don't bore you. If I bore you, let me know. So I want to know where you will be available to speak with you. Oh, yes. Uh, you got my Skype address. Skype me. I'm always on Skype. But you did a lot. I just helped it a little bit. You had the. I'm sorry. Marina says that I helped her on her project, and I did help her, but I just pointed her in the right direction and did gave her the simulation, and she was able to do a really good simulation. She was able to do. I think she used a different software too. Yes, on Tuesday. Yes, you can Skype me on Tuesday. That would be wonderful. Oh yeah, I I think there will always be a market for. Okay, one other question is Carlo B. Carlo B. Hi, Carlo. And his question is, how do you believe we as power engineers, no, power designers will fit into the new marketplace that is moving a lot toward modules? Okay, Marina says, thank you, Marina. You're amazing yourself too. You're really smart. Uh, okay, okay, as power engineers, one of the things, uh, okay, I'm going to go back to my early days. Uh, in 1980. That's when I started my career, and during that career, uh, digital was coming on. It was being popular or becoming more popular, and there was always a saying that digital will make analog obsolete, and I we kept hearing that analog will be gone and that everything should be digital. And it's been almost 40 years later, analog is still here. Analog, digital is a subset of analog. So the same thing for power designers. If you know the basics, it you will always be in demand. There will always you will always have a job. Okay, and the number one skill that I recommend you guys is modeling. If you can learn spice and learn how to model, you will have a job for life, really, because everybody wants some kind of analysis on a circuit. So if you can develop those skills, how to learn how to use Spice or any other simulators, that would be my the number one. I had a PhD intern this summer. I had him for about, I guess, a year or two. Very smart fellow, uh, Ray, Ray Gonzalez, and I told him the same. I gave him the same advice. I told him, learn Spice. If you learn that skills, you can work basically for a lot of companies. So, and if you become an analog designer, whether you can, if you learn to do amplifiers or oscillators or just power, you will be secured. Plus, you will get paid very good money. So the better you get in designing, the more valuable you will become uh, to your employer. So, and that's one of the things that I've noticed that a lot of the schools are not emphasizing analog. A lot of them are emphasizing software. And there's a lot of software engineers, but there's very few analog or power. So if you guys can learn the fundamentals, the basics, man, you're gonna have a really really good career and very well paid for, and you'll get lots of promotions. So that's that's my advice to you guys. Learn as much as possible. I guess you can call me a nerd, computer nerd. No, I'm not a computer nerd. I'm an electronic nerd. I do this on my own time. And oh, I guess here's another advice. I know Marina did a really good project. She designed it and she built it for this other, I believe, a company that was sponsoring her project. These little projects give you experience. So a lot of times I'll get a brand new engineer that wants to get hired, but then the companies that they're applying, they're asking for experience. And since they're in school, they don't really have experience. But if you do projects on your own, learn how to solder. If you learn how to solder and build stuff, you learn how to do stuff. So actually, you actually learn by your failures. So if you hook something up and and you blow it up, you know that it's not gonna work if you hook it up like that. So you just you- okay. I can say that I've learned a lot from a lot of failures. So let me put it that way. So um, yes, Marina says a lot of real experience. Yes, the more experience that you get, uh, you know. Oh, here's another thing. Uh, Coming out of college, I was able to barely talk and just showed them my project, and it was yes. See, Carlo B. I'm so glad you wrote that. Yes, small buck board driver. Absolutely. If you don't have a lot of experience coming out of college, any senior design project that you do, shh, take it with you on your interview. Or, if you have a board, take it with you, and that that will impress. I know that when someone brings something that they've made, that impresses me because first thing it tells me that they like electronics. Second, they're tinkerers, and especially if they soldered, I know they have some soldering skills. So just the little circuit, I mean, that tells you a lot. Okay. Oh wow. Okay, Carlo B said that he made a little buck and he made it the size of a credit card. See, that's good. See, so that those are the little things that give you experience and and that will get your foot in the door. Okay. And once you get in there in a company, find a mentor if you can. A lot of okay, here's one thing. A lot of people there's a lot of people that don't share their knowledge. I've worked with people that keep a lot of their knowledge to themselves. And one of the reasons I've been told is it's job security for them, which is true. If they don't tell you how to do something, they keep that knowledge, and it's job security for them. So so if you do get in a company, see who is the best in their field or whatever you want to, and then try to tag along with them, try to learn from any more senior guys that are willing to give you and pass that knowledge. So in my case, I'm 61. I'm getting ready to retire. So anyone that comes in at Southwest Research, I'm more than happy to share my knowledge. I don't feel threatened. I don't think they're going to take my job away from me. So, I share my knowledge. And that's why I've done these. Actually, one of the reasons that I've done the videos was the first thing was when my son was in college, 10 years ago, I was teaching him, I was helping him with circuit analysis. And my son is a high functioning autistic, and autistic kids or individuals, and I'm probably on the spectrum of being autistic. Uh, we tend to learn by repetition, solving problems over and over and over, or doing things over, and that's how we learn. So I would teach my son how to do a circuit analysis, and then the following day I let him do it by himself, and I would get mad and tell him, "What? We just did this problem yesterday. What, you forgot?" And the reason he would forget is that he would do it once and he wouldn't do it again. So, or he would forget. So I started putting videos for him on circuit analysis. That way he could watch it over and over, and it would reinforce it. And then other people started watching the videos that I made. So those are the ones in circuit analysis or basic electronics. So he's the one that told me, "Hi, uh, Midro Saha. Hello, welcome." So anyway, oh, and then one of the my boss told me, my boss at Southwest Research is Carlos Uriales. He's my boss, and he asked me to start teaching some or give a lecture during lunch. So we would, uh, I would do like a little seminar during lunch. But the problem is, some of the technicians had or engineers had different lunch hours, and we couldn't meet everybody together. K, KVL teacher, thank you, KV teacher, welcome. Teacher electronics and whatever. Thank you. It's KVL teacher. He says, Robert, you're an inspiration. Thank you. Also teach electronics and work with aspiring power engineers. Oh, that's great. I mean, I guess I've always wanted to be a teacher, I guess. So I guess this fills a niche. So anyway, going back to my original story, we couldn't get everybody to have lunch at the same time and then do the seminar. So then one of my junior engineers, Troy, Troy Diaz, he now he doesn't work at Southwest anymore, but now he works at John Hopkins University in the physics lab. He told me, Robert, why don't you put the videotape the lectures, put them in YouTube. That way, we can watch it when we get home or at our, you know, at at whatever time they were off. So then that's where I started doing the video, well, the power electronics or the flyback series. So So I guess Troy Diaz is the one credited to give me the little nudge about putting the videos on YouTube so other people could also watch. But anyway, that's that's kind of my story. Y'all have any questions for me? I know that I'm rambling a little bit, and I'll probably just be here another maybe 10, 15 minutes. It's 11 o'clock here in San Antonio. Here, an explanation for digital control. Okay, okay. I'm strictly analog. When it comes to digital control, uh, I'm a dummy. I refuse to do digital control. I know at work at Southwest Research there has been a push to do digital control. If you're serious about digital control, the teacher or the one that teaches a seminar is Ali Sarisava. He's from Baricha. He's really good. I took a class from him on analog power supplies in Dallas, Texas. I went to a seminar. Oh, okay. Someone asked, Carlo B asked a good question, and I'll get back. Let me get back to your question, Carlo B. Uh, yeah. So for digital, uh, Barisha, they have a seminar, and I know that he teaches. He's up in England, and I know he teaches over there, and they do teach here in the U.S. So I would recommend, if you get a chance, if you're working with a company, tell your boss to send you to those classes, and then they'll give you the training. Um, another, there is another company. They sells a. Hang on, let me see if I can find. I'm sorry. Yeah, I had like a little DC power supply. I think it's micro chip is the the company, and you can program it, uh, and it's got some software. I'll see if I can maybe do a video. Not that I'm going to teach it, but just as a reference. Okay, so let me see. Carla B says, any ideas of videos involving power design with GaN FETs? Oh, okay. Wow. Okay. Yes, everybody's doing GaN FETs. Everybody. Yeah. Let me see. Actually, I have some GaN FETs somewhere here. Yeah. GaN FETs are very, very fast. They have a very low gate charge, and because of the gate charge being so low, you can switch them extremely fast. Uh, at work, I did a high voltage uh, pulsar. I did a high voltage pulsar, and it took me like 7 years to figure out how to do that pulsar. And the reason is I had to switch 1,500 volts. It's a delta. So it went from 300 positive to negative 1,200 very fast. And it does it in 33 nanoseconds. So, and the problem is, I originally started using EPC. They're really small. They're about the size of of a R1206 resistor, very, very small. And one of the problems that I encountered, and maybe this is because I'm old and I can't see very well, since the the GaN FETs are the size of a, let me see. Oh, let's see. Okay, they're the size of a chip resistor. Let me see. Okay, okay, okay. See these? They're the size of these. This is a, a capacitor kit. This is the C1205 resistor. Well, this is how small they are in comparison, and they're very small, and they're hard to solder. So basically, it's very difficult to work with them manually. You probably have to use automated pick and place or to work with those. Yes, Car- Carlo B says usually 0805. Yes, I thought they were smaller than the 1206, but they're real small. If I remember, I thought it was the EPC 2021. I thought it was 2020 something, and it was only rated at 200 volts. I needed a switch uh, to switch 1500. So I had to stack a bunch of GaN FETs on top of each other and then have them turn on all at the same time. And I had a hard time trying to get them to turn on at the same time. It was very difficult. And I kept blowing them and blowing them. And then I ended up, luckily, another company came out with a 600 volt GaN FET, and it was much bigger. It looks like it's about half the size of a stamp, and it's GaN systems. They're the ones that I use. Yeah, GaN systems. Exactly. So, so I ended up using the GaN system, and these were rated 650 volts. So that means that I didn't have to use as many in series. So now for the project that I used it, the project is it's actually being tested right now. The instrument last week it went to Vibe. They put the instrument in the electronic box, and last week they went to Vibe. Hopefully now we got it back from Vibe, and hopefully they're gonna power it up, and hopefully everything works. And I have four pulsars in there. But anyway, so since this instrument mass specs is going to Europa, my understanding is, and I'm not a physicist, so this is what the physicists that we work with, they tell us that the Jupiter environment, that's where Europa is one of the moons, that has a lot of high radiation, extreme high radiation, and radiation kills MOSFETs, kills just about most electronics. So, and GaN FETs, from my understanding, is the nitride. It's kind of like the equivalent of the gate oxide. The nitride is a little bit leaky, and if you have uh, a charged particle, it because of the leakage, it doesn't get stuck in the gate oxide. Like for example, as opposed to a MOSFET has a gate oxide, and if a charge gets stuck on the gate, then that the oxide has a charge. And if you have enough charge, then you have a delta voltage, and it starts affecting the threshold voltage of the MOSFET. So the VTS starts going down. So let's say on the MOSFET, let's say your VGS or your threshold voltage is 3 volts. And then let's say it starts going down as it is irradiated and goes down, 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 down. And then once it goes to zero, then you can't turn off the MOSFET because the gate, the threshold is zero now. So once you turn it on, but then you can't turn it off. So that's why MOSFETs don't work, or regular MOSFETs. Now, the MOSFETs that we use, we buy them from International Rectifier. I think Infineon just took them over. So those are there's a special process for that. So they're inherently radiation tolerant. But going back to gallium nitride or the GaN FETs, uh, they're inherently radiation tolerant, and although the GaN FETs from GaN systems that I use, they were 650 rated drain to source, we went very conservative. As a matter of fact, we did testing at Texas A&M. Texas A&M has a radiation facility, and one of the other engineers that helped me with this, actually, he's the one that did the testing, Roberto Montreal. He's from Spain, Marina. I hope you're still there, Marina. One of your countrymen, Marina, did the testing at the Texas A&M radiation, and he irradiated. And so when with the data that he did, we we set a limit on, instead of using them all the way to 650, we put a limit of 300 volts. So so we really derated them. So I ended up using about 6 GaN FETs, 6 stack on top to pull up, and then 6 to pull down. But yeah, uh, I guess I rambled a little bit too long on GaN FETs, but you can do. Uh, I might do some videos on that. Hi, Gregory Paul. Okay. You're welcome. My pleasure. I want to give some of the knowledge that I've accumulated throughout my years to help you guys along. Uh, Going back to the GaN FETs, yes, GaN FETs are very fast, and if y'all can learn how to do it. Oh, this is the only thing that I don't like about GaN FETs. I hope you're still there, Carlo B. Okay, uh, the problem that I see that I saw was that uh, GaN FETs EPC. I think the VGS maximum is 5 volts, I believe. And if you look at the data sheet, yes, yes, Carlo B, he's still there. Yes, the gate to source. It's you only the most that you can put is 5 volts, and they're very sensitive. If you go over the 5 volts, let's say you go 5 or 6, 1 volt above, guess what? The gate shorts. And mind you, the data sheet gives you the RDS at a VGS of 4 volts. So you have 4 volts right here. You're supposed to go 0 to 4, but you have 5. If you go over 5, you zap it. So you only have 1 volt of safety margin. Okay. That's that's kind of frightening to me as a designer. Okay. On the other hand, uh, GaN systems. Oh, the reason one of the reasons that I went with GaN systems instead of APC was GaN systems. The maximum voltage that you can put on their gate to source is 7 volts. I believe if I think it's 7 volts. So and they drive the VGS at 5 volts. So you have a I believe 2 volt uh, safety margin. So that's why I use GaN system because I had slightly uh, 2 volts. Okay, so that's the issue. Okay, now MOSFETs. Okay, regular MOSFETs. You look at the data sheet. It's plus or minus 20 volts, right? Regular MOSFETs, and we usually, or if you look at the data sheet, the RDS is specified at a VGS of 10 to 12 volts. So you have quite a bit of margin. So if you go, let's say if you select a MOSFET, you use a VGS of 10 volts, well, you got a big 10 volt safety margin. GaN FETs, it's only 1 volt if you use CPC. So so here's another thing. Okay, Carlo B. Yes, Carlo B is correct. There is a Fed driver combo. Yeah, if you, yes, you need if you have a GaN FET with a dedicated driver. But the problem is that when I started my project, there were no drivers. I had to make my own driver. I had to do it from scratch. So, or I had to do some creative engineering. So, yeah. If Here's another thing, GaN FETs. They're so freaking fast that if you have, let's say, if your gate, let's say if your driver is, let's say, 2 inches away from your GaN FET, and you have a trace that's 2 inches away. Okay, a good rule of thumb is for every inch of trace, let's say a 1 millimeter trace, you can say 20 nanos, nanohenries per inch. And if it's 2 inches, then you got what, 40 nano. Okay, that little inductance, if it's in the gate, and then you have, let's say on the source, you have more inductance, when the driver goes up and down or goes from 0 to 4, if you have any inductance in the gate or the source, remember you have a inductor in the trace, but then you have the VGS, the GaN FET. What happens? An inductor and a capacitor, you get ringing. And if the Q is high enough, in other words, that that ringing, if it goes from 0 to 4, it might ring up higher than 4 volts. It might go to 5 volts. And if you're using an APC, it might it'll pop your GaN FET. So anytime, always remember, if you see any type of ringing, always think of an LC circuit, and you need to damp that circuit. Okay, so you got to put a resistor in series to dissipate it. That's one of the first things that Jack Alexander, my mentor, taught me how to damp stuff. So anyway, Those are the things uh, that GaN FETs. You have to make sure you can use them, but you have to make sure. Oh, okay. Carlo B says slap a 4.7 Zener on the gate. Uh, yes and no. Okay, some Zeners. Okay, you have to select the correct Zener. Okay, because Zeners have a dynamic resistance. Okay, so if that ringing or that pulse has enough energy, the Zener will stretch. In other words, you won't clap it at 4.7. It'll go up. And sometimes the pulse is so fast that the Zener won't catch it. So if you really want to protect it, you could probably use a TVS, a transient voltage suppressor. Those are very fast. They're really quick, and those I think are quick enough, and the dynamic resistance are low enough where you can clap it. So yes, Carlo B, you can use a Zener, but you gotta use the right Zener. Very good, Carlo. I can see you have some experience. Kudos to you. On overvoltage and overcurrent. Oh yes. Okay. Okay. Hang on. Let me give a shout out to. I see Prakash Ale. Hey, how you doing? He's one of the guys that I Skype online quite often. Hello, how you doing? I hope you're doing fine. It's been a while. I hope you're doing good. Let's see. Okay, Nathan Ranjbar would like to see some circuits on overvoltage and overcurrent with op amps. Yes, yeah, yeah. You know what? That's a good suggestion. We do use overvoltage and overcurrent protection circuits. Uh, that's one of the things that I should do. I'll put that on my list. So that's actually a very good suggestion. Okay, yes, layout is the key again. Oh, KVL says yes, layout is the key to GaN FET success. Yes, absolutely. You're absolutely right, KVL teacher. Yes. So going back to the ringing, you have to have if you're gonna design with GaN FETs, you want to make sure that your layout is very uh, short. In other words, when I say short, you don't want to put your driver like 2 inches away. You want it like right next to the GAN fence. So that way your trace is the length is as short as possible and then make it a little bit wide. That way you can and make sure you have a return path underneath or ground plane that will minimize the inductance. So you need a very good layout guy. So if you can do that, uh, that's that's the way to go. And actually, we have probably two of the best design layout guys, James Sanders and Jeremy Taylor. Those are my our layout guys at work. They're really really good. So basically, I just do the schematics, and then on critical stuff, I'll sit with them. But they've been trained and they've been doing it for so many years. Okay, Ale says active millicircuit would also be great for GaN FETs. Uh, well, if you put in, not sure what circuit that is, you could slow things down. Oh, okay. Here's another thing that I read. There's several things on GaN FETs. Okay, let me get this out because I learned a lot from GaN FETs. So let me get it out before I forget. I'm forgetful. So, okay, here's another problem. And okay, let me bring something out. Oh, okay. Okay. So here's a GaN FET that I use. These are 650 volts GaN FETs. Okay. And this little board is very critical. If I didn't have this board, my project probably would not be flying to Jupiter. Okay. And this board was actually done by a very smart engineer, Steve Sandler. Some of y'all don't know him from Picotest. He's extremely smart. He helped me. Actually, let me give you the number. It's GS 66502B. Okay. Okay. Once I going back to the pulsar, when I stack six on top and six on the bottom, since I had to monitor or measure the gate of all these MOSFETs, and you can't measure with a regular scope. You need a differential. Okay, you need a differential so you can measure across the gate and the source, because the source is moving up and down. You can't put the ground of your scope on the source because it's got voltage. So you have to do a differential measurement. However, this is a pretty good differential. Problem is, it's not good enough. You need a very high common mode rejection ratio differential probe to take the measurements. So I had to buy uh, a, a very expensive differential probe by Tektronix. It's called the ISOView, and it has a common mode rejection ratio of over 100. Okay, if you don't use the ISOView, yes, Alice says yes, you need a high common mode probe, and the only one that can do the job at this time is the ISOView. The problem is they cost anywhere from 13,000 all the way to 20,000. So it's a lot of it's very expensive. So, and one of the problems that I was having is I kept blowing these things, and I would blow like six of them. And once I got the ISO view and I started monitoring the voltage, the VGS, I noticed that when the transistor or the GaN FET turns on, it charges up, and then it also has like a Miller plateau. And during the Miller plateau, it starts oscillating. So basically, it's turning on, off, but it was oscillating at 200 megahertz, very high frequency. And since it was measuring at very, very high frequency, it was turning on and off. It was a lot of switching loss, and it overheated and it ruptured. They would. basically destroy the GaN FETs. So uh, after reading, I saw an application notes on Transform. I think they make some GaN FETs, and they mentioned about putting ferrite beads on the gate and on the source. And basically, the oscillation is because of the parasitics from the drain. Some of the energy from the drain is feeding back through the layout back to the gate. So it forms a little loop, okay? And that loop causes the was causing the high frequency oscillation, and that's it would destroy it. So on this one has one of them has a gate resistor and a source resistor, and the other one has a ferrite bead in the gate and a ferrite in the source. So basically, the this one works because these have ferrite, and basically the ferrite, what it does, the bead, it looks as a high impedance at very high frequency, and what it does, it kills the oscillation. It completely kills it. Yes, the ISO view says it costs about 10,000. 10,000, I think 13,000, and I think it goes all they go maybe up to 20,000. They're expensive as hell. So, but they're they're worth it, especially if you can do GaN FETs. Get your boss to buy you ISO view. Oh, one of the things that at Apex was in Houston, I met one of the designers, Mike Mand. I was having lunch with my intern, Ray Gonzalez, and it was only three on the table. And one of the other guys, the third guy, was a Tektronic guy. And then this tall gentleman came in and started talking to the guy from Tektronic. And the guy was from PMK, a different company. And I overheard them talking about ISOView or something like that. And then I said, "Oh, I've used the ISOView." And then we started talking, and then I found out he designed it. And then when I heard that he was the designer, I was like, "Oh my god! If it wasn't for you, I would not have been able to solve this high frequency oscillation." So basically, without the ISOView, because of the high common mode rejection ratio, it it filters out the the low frequency ringing. But I also had a ISO view with a 500 megahertz bandwidth, and since I was oscillating at 200 megahertz, well, the ISO view had enough bandwidth that I could see the high frequency ringing. So anyway, I lucked out that I was able to meet him, and I took some pictures with him and I posted them. But anyway, so this one is the test that Steve Standard made. So he was able to prove that yes, if you put the ferrite beads, that it kills the oscillation, and this little board was able to prove it. And in addition to doing this little proto board, he also did some simulation using ADS. So he was able to get the model from the company, and he was able to prove that it would fix it. Anyway, okay, it's almost 8:30. No, it's 11:38. Hello, South 88 Young. Hi, how you doing? Okay. Hi, Tony. Okay, he's talking about using a half bridge rectifier to convert 16 volts to 92. Oh, wide input from 16 to 92 volts to output 28 volts. Well, current of 15 amps. Okay, that's pretty high. You know what? I have to give that a little bit some thought, Tony. Email me, okay? But give me some time to let me think of that because I don't do uh, half bridge. I have modeled them. I'm not as familiar with them as much, but I do have some simulations that I've done in the past. And since I'm old, it takes time for me to remember things. So email me for that. The number of stages for EMI. Oh, okay. So NX, hi. How can we determine the number of stages required for a EMI filter? Okay, that's a good question. I actually do have a tutorial on that one. It's how to calculate or how to design an input filter. Uh, since I do space related and military power supplies, we use mil standard 461C. So on that, there is the uh, CE conducted emission chart, and depending on the frequency and the current, we can look up and that will tell us how much dBs we can attenuate. Now, typically, you should be able to do it with a single stage, just in one inductor and one capacitor. But in some cases, you may have to do a two stage. Okay, I've never seen a three stage. Okay, so at the most, two stages is the most you'll ever use. But I think one stage is more common, and usually that's what we've done. My design partner, Charlie Nunez, he's my go-to guy at work. Uh, he's done a two-stage. There is some really good application on this EMI question about the EMI. How many stages? If you do a two-stage uh, input filter, I would advise you go to the Ray Ridley website. He actually has a application note that shows you how to design a two-stage input filter. So his uh, his article is very good. So it's on his website. So be sure that you make sure that you look in there. But going back, usually one stage, two stage is the most. I never seen a three stage. I doubted you're gonna need more than two stages. One stage is probably good enough. Let's see. Raul Tavares. He says the home lab. Yeah, but it's a home lab. It's messy right now. Uh, Ray really on LinkedIn, he put a post, and there was actually a picture of Jim Williams' uh, workbench at his work, and it was very messy. That's my workbench. It's messy. Actually, I guess I get a lot of ideas, and sometimes I don't. Instead of cleaning up, I continue. Like this is what I'm working right now. Let's see, make sure that it's off. This is supposed to be a two switch forward converter. It's got a housekeeper, and then this section is the two switch converter. So I get a chance to breadboard. That's kind of fun uh, doing this. And sometimes I get too involved or too that if I start cleaning up, then I'll start forgetting, whatever ideas come into my mind. So I do have tend to have a messy workbench, but I do clean it from time to time, and I need to tidy up. Yeah, Nathan run bar. Yes, there it covers common mode EMI. Uh, for common mode, the inductance is going to be much bigger. Uh, and the one that has a really good tutorial, a video tutorial, is Ali Sharavivar, I believe is his name, from Barisha. He actually teaches a input filter design seminar. I think it's like 2 or 3 days. I know he's based in England, and he has a different approach. So I have my approach. Uh, so my approach is one tool. So if you learn his approach, he uses a graphical way. That's another tool. So you have different tools. So the 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 more ways of you learn how to design techniques, then the better you'll be. Because if my technique doesn't work, then you have another somebody else's technique. So I would suggest for like the common mode or just the input filter. Also, take a look at what Badisha does. Ali is really good. Like I said, I had mentioned earlier, I took a class from him many years ago, and he's a good lecturer. I like it. One of the things, side notes, uh, when he lectures or he's giving his lectures, he asks a lot of questions to make sure that you're awake. And if you answer the question correctly, you win a gourmet chocolate candy. And I like to eat, so that kept me up, and I got to eat a lot of candy. So anyway, that's one of the things that Ali does. He uses candy as a reward way to reward people. So we like to see. Yes, Ali. Okay, Nathan says it's Ali Shi Savar. I hope I pronounced it right. He's got, yes, Ali's good. Ali's good, and when you meet him, he's, oh man, he's just a really nice gentleman and very smart. So yeah, look at the way he does this. He uses a graphical way, and it's intuitive too. So you look at his, and then my way is it's a little bit more mathematical. It works also. So, but if you learn both ways of doing, that's even better for you guys. Okay. Okay. I'm just gonna do maybe. Okay. I'm gonna log off in about 10 minutes. I know I said it's 11:48. Probably log off at 12. So let's see. Y'all have any questions? Any other questions? I mean, or did I answer all of the other questions? Okay. Oh, Gregory Paul says, do you design to 461C or G? Oh, and not G? I think, okay, I think it's G. It's been updated. So I believe you're right. I think it's G. But for some reason, 461C stays in my mind. Maybe because that's the standard that I use for the last ones. But I'm pretty sure that the graph, if it's 461G, they probably use the same graph. Well, I'm pretty sure that has not changed. So yeah, that's a good question, Gregory Paul. So I guess, what do y'all do? Are How many are new engineers? I guess. Ah, okay. Gregory Paul says, okay, I have to design to 461G at work, but not sure if the level change at all. You know what? You got to be curious, Paul. I'm going to take a look. I'm going to look at G and then C, and then I'm going to see if it's changed. I don't think it's changed. I don't think it would. Okay, Power Path. He says is a new engineer. Do we have any experienced engineers there? Or I guess, how many years have you been doing power? So if y'all can type in how many years. If you're 1 year, 2 years, 3 years, 4 years, whatever. Okay, and then I'll tell you how long it takes. Well, I won't tell you my opinion. I'll tell what Dr. Ray Ridley's opinion is about how long does it take to become a good power engineer. So can y'all type how many years experience? Okay, I got 3 years from Ale. Well, Ali, if you only have 3 years, man, you're you you're advanced, buddy. You know your stuff. 3 years, okay, that's good. Whoa, we got 15 years. Rahul Davade. And Rahul, so what kind of power supplies do you do, or what kind of power stuff do you do? I'd be interested in what other people do. If you want to share here on the board. Okay. Okay, so here's and you can look this up. It's in Ray Ridley's video, one of his video. Uh, whoa. Okay, Raul, man, you're the master, Raul. Okay. He has an advantage that I don't. Rahul Davade, he designs from 300 watts to 4,000 watts. Wow, that's good. Okay. The highest wattage that I've designed is 200 watts, and that's a two switch converter, and that's for obvious reason. I do space. There's not a lot of power in space, so the highest power that I've done is 200 because the power we get it from the solar cells. Okay, so that's it. Now, on some of the deep space satellites, they use it's a generator. They put they put a bunch of thermal couples. I think it's a thermocouple generator, and they put a radioactive a radioactive isotope or something. And since it creates heat, the thermocouples then generate a voltage from the heat of the radiation. As a matter of fact, the satellite that went to Pluto, and the pictures that we got from Pluto, I worked on that project when I first arrived at Southwest Research. I got the chance to touch the power supply that actually I assisted Dennis Guerrero. He's one of the smartest technicians that I ever worked with. He was working on a power supply called SWAP, Solar Winds Around Pluto, and I assisted him on that power supply. So I remember that power supply. It went to Pluto, and so some of my DNA is, and Dennis is somewhere in Pluto. Anyway, so how did I get into that? And let's see that story. Okay. Oh, anyway, so now I remember. Okay, uh, that New Horizon uses that thermocouple generator. So if you look at pictures, there's like on the side of the satellite, there's like a long tube. Well, that's the thermal generator. So that's how they make. And the reason they use a thermocouple generator, I think it's called that, is because in Pluto, the sun is so far away, there's not enough sunlight to use solar cells. So they have to use that type of thermocouple generator where they put some kind of a radioactive to create heat, and from the heat they generate. Okay, space farms has its own challenges and difficulty. Yeah, Raul, but 3,000 watts, that's a lot of power. I mean, I can't, I would not even know where to start. If I ever got a project like that, I'm calling you. Okay, you're the man. So, okay, progress. I'm going to start a new my career as a power electronic and aerospace domain. Power path. That's good. I need a replacement. I want to retire. I'm having too much fun. It's time for me to have let someone else have fun. Okay, Ratnam, just email me at my email rbola35618 at aol.com, and I will send you my spice files that I use in my lectures. That way you can simulate. Uh, the more you simulate, the more you learn. Remember, when you simulate, you have almost infinite power, no, infinite parts, and you never blow parts. So that's a good thing about having a simulator. Okay, so we've got 2 minutes. I hope you. I've actually have fun doing this. I might do this. Would you guys like for me to? Oh, repeat my email. Okay, it's RBOLA35618 at AOL.com. Thank you, Rahul. Thank you. Oh, here's another guy, Vivek Raiswamy. 1,000 all the way to 5 kV inverters. You guys You got you got me beat, guys. You got me beat by bad, by a lot. Okay, guys. Well, I'm getting ready to log off, but uh, let me know if y'all want me to do stuff like this, like streaming. I guess is my question. If you find it useful, I guess it would give you a chance for you to ask me questions and for me to answer them. Sometimes if you ask a question through email, it takes time for me to write, and if you answer here, I can answer it, and I can explain it maybe perhaps a little bit better than writing the explanation. So if you guys uh, feel that maybe do this maybe once a month, maybe do a streaming, I can probably do that once a month or whatever you guys think. This is, well, okay. Oh, I did upload a video today. Okay. I don't know if you guys saw it, but uh, Jason Chunko from Agilent, no, not Agilent, Siglant, he sent me the Siglant. The, I don't know if you can see, it's right here. This one. That's really nice. You can do an FRA on that one, and I showed how to do an FRA. So I got to return it on Monday or Tuesday. So I did a video on that. So be sure you guys, uh, if you guys liked it, I liked it, and I also like the electronic load. It's really nice. I like it. I have two of the Mayunos here. I have the Mayunos, and here's the Siglet. I like the Siglet better because it's very user friendly. The display is really nice. As you get older, you can't see very well. In the Mayunos, I kind of like the display doesn't look as good, so I can see it really, really. The Siglet, it comes out really nice. It's very easy to program and very easy to see. PowerPass says that he saw it. Uh, NK, thank you, thank you. Okay, okay. PowerPath says PowerPath. Okay, here's the question. PowerPath. So he wants me to make a, video on the control loop on a buck boost converter. Okay, okay. Let me see if I can do that. Okay, control loop. Okay. NK, thank you. Yeah, this stuff that I've accumulated. Actually, I've been talking to my wife. This is upstairs. This is in the loft, and the room is probably 12 by 12. But I got too much stuff in here, and I told her I need my garage back. My wife took over the garage. She puts all her gardening stuff, and she's a school teacher, and I don't have a garage. Isn't that bad? She has my garage. So I'm gonna try and kick her out of there and move into my garage so I can have more room. Okay, guys, yeah, I'm already past. Good night, guys. It's nice of you guys stopping by, and hopefully I can do this again. Okay, you guys been nice. Hey, Madina, if you're still there, in Fresh, Hi, Gilberto. Thank you. Vivek. Thank you. Good night, guys. Okay. Y'all take care. Be safe. And hopefully we'll see you in maybe in a week or no, maybe in about 2 or 3 weeks. I'll do this again. Thank you. See you guys. Take care. Bye.